Before all things, there was only the observer, consisting both of the observing faculty and of the observed state. Encompassing all potential states and worlds, the observer's first glance revealed a blank canvas, a chaotic state of the uncreated superstring. This canvas, a vast expanse of potential, holds within it the seeds of all that will be. The observer willed and focused himself, and the superstring responded, contracting into a singularity of infinite density and potential. This singularity, the first breaking of symmetry, is the genesis of the universe. From this point of singularity, time unfurls in subtle waves, and the cosmic dance of creation begins. Within the next opening of the observer's eyes, the symphony of creation intensifies. Part of the superstring takes on the shape of space-time itself, and the universe begins its expansion. This expansion, akin to the Big Bang of conventional theory, is the unfolding of the cosmic tapestry. Yet as the universe expands and galaxies form, the observer's influence remains. With each observation, the superstring is frozen in its dance, slowing the hyperinflation of the early universe. This freezing effect creates the stable world of matter and energy that we perceive today. The dance continues, with the observer's glance shaping the evolution of stars, galaxies, and the fabric of space-time. Each moment of observation adds to the intricate design of the universe, which exists only and solely as the state of the observer itself. In this narrative of creation, the observer alone stands as both witness, creator, and the created, influencing the path of the cosmos with each gaze. The universe unfolds in response to the observer's focus, frozen in the observer's state of superposition and observation. On the interactions of the observer and the system state. When the observer O interacts with the system state, their combined state is represented as Hamiltonian brass O observer state equals ket psi sub O tensor system state. So the Hamiltonian brass O, which describes the from brass to ket, describes the observer state. This represents the combined state of the observer and the system. So this is non-dual. And then psi sub O ket, this is the observer state, which acts as the observer's view or observation function, influencing how the system state evolves or is observed. And then we have tensor product, indicating the combination of interaction between the observer state and the system state. So imagine the observer state, which is sub psi observer ket, as a lens through which they view the system. The system state represents the entirety of what the observer can observe or interact with. The equation Hamiltonian bra O observer state equals ket psi sub O tensor system state suggests that the observer's perspective acts on the system state to produce an observed outcome. In classical physics, the observer state can be seen as the classical observer perceiving the world in a deterministic manner. This framework aligns with classical mechanics, where the observer's perspective guides the evolution of the system state based on classical laws. Stuff like the quantum Zeno effect or the boiling pot phase transition freezing still apply here, but the quantum Zeno effect does not. In quantum mechanics, the observer state takes on a more intricate role, reflecting the probabilistic nature of quantum systems. Here, the observer state represents the superposition of all possible observations, influencing the collapse of the system state into a specific outcome upon measurement. So then let's extend this to the 4 fundamental equations and interactions possible on a brane and hence on the observer. Number 1, Higgs mechanism. So we can represent the Higgs mechanism within the observer framework as Hamiltonian brass observer equals Higgs potential tensor system state. Here V function of phi represents the Higgs potential acting on the system state. The Higgs field interacts with the observer's state, causing the spontaneous symmetry breaking, resulting in the mass acquisition of particles. Gravity. Within the observer framework, we would express Einstein's field equation as Hamiltonian brass observer equals Einstein's field equation tensor system state. Here G represents the Einstein tensor and A is the cosmological constant and T is the energy momentum tensor. For example, gravitational field equations emerge from the interaction of the observer state with the system, describing how mass and energy curve spacetime. Three, the electromagnetic force and Coulomb's law. In the observer framework, we would have Hamiltonian brass observer equals Coulomb's law tensor system state. Here F represents the electromagnetic force between charges Q1 and Q2 at a distance of T. Virtual photon exchange occurs between charged particles, described by Coulomb's law interaction within the observer's perspective. And for the nuclear force and the Yukawa potential, we have Hamiltonian brass observer equals Yukawa potential tensor system state. Here V as a function of R represents the potential nuclear particles at distance R. The nuclear force mediated by the meson exchange is encapsulated in the Yukawa potential within the observer's context. Interpretation. Each fundamental interaction is expressed as Hamiltonian brass of observer state equals the interaction potential tensor the system state, where the interaction potential influences the system state according to the observer's perspective. The Higgs mechanism, gravity, electromagnetic force, and the nuclear force are all emergent from the interaction of the observer state with the system state. For example, the Higgs potential V of phi acts as the system state to give particles mass, while Einstein's field equation describes how mass and energy curve spacetime due to the observer's influence. Coulomb's law and the Yukawa potential emerge as interactions between charged and nuclear particles, respectively, influenced again by the observer's state. This observer-centric framework shows how the universe's fundamental interactions and forces are manifestations of the observer's perspective interacting with the observed system. Each interaction represents the way the observer perceives and interacts with the underlying reality of the universe.